Okay, so let's look at a little bit of review here, covering details regarding increasing and decreasing functions in the first derivative test, looking at linear approximations and the relationship to the concavity of graphs, and working with what graphs have to look like and what tangent lines have to look like based on understanding the first derivative and second derivative of functions. So here I have a function. The function is e to the 2x times x to the fourth power. I want to find the critical numbers. I want to find the interval when my function is increasing or decreasing, and I want to apply this first derivative test. All right. Well, my critical numbers is going to be if f prime is 0 or if f prime does not exist. Right. I know that if f prime is greater than 0, then f is increasing. Right? And conversely, if f prime is less than 0, then f is decreasing. Okay? And for my first derivative test, I know that that sets up that if f prime changes positive to negative, I have a relative maximum. And if f prime changes negative to positive, then I have a relative minimum. And in general, your justifications are much better thought of before you start your work. So let's go ahead and start our work. We know that for our critical numbers, we're going to need to find our derivative. So using the product rule, f prime of x is going to be the first times the derivative of the second plus the second times the derivative of the first. Right? If I factor e to the 2x out of both of these, and really I have e to the 2x times an x cubed I could factor out of both of them, then I'm going to be left with 4 plus 2x. All right? So technically I could have factored out a 2 as well, but I just need to factor a little bit. All right? So we need to find out when that's equal to 0, and that's going to be if x is equal to 0 or if x is equal to negative 2, right? Because we're trying to figure out, does this ever equal 0? And that's going to be if x is 0. Or does this ever equal 0? And that's going to be if x equals negative 2, right? Using the zero product property. Now we know e to the 2x is actually never going to be 0. E to the 2x is always going to be positive. So our critical numbers, x is 0, x is negative 2. Now, how can I figure out if my function is increasing or decreasing? Well, one way to do it is to do a sine analysis. All right, so I can do a sine analysis on my work. And I know that I'm equal to 0 if x is 0. I'm equal to 0 if x is negative 2, right? And we're talking about my derivative because I'm working with my critical numbers. So my derivative is 0 at 0, and it's also 0 at negative 2. Now notice that this multiplicity, right, is equal to 3 because the exponent there is 3. And this multiplicity is equal to 1 because I just have this implied linear term there. But what's important for us is they're both odd multiplicity, right? So if they're odd multiplicity, right, the sign will change with odd multiplicity. Right? That's that idea that if I have a graph of a function and the function bounces at my axis, then I'm going to have an even multiplicity. But if the function comes through and goes through my axis, I'm going to have an odd multiplicity, right? So if I said that this was A and this was B, this function might be given by x minus a squared times x minus b to the third power. Even multiplicity, don't cross, don't change sign. Odd multiplicity, I cross and I change sign. Now, notice that when I put this up, I have 0 and negative 2. Well, this isn't the order that I have 0 and negative 2 on the number line. Negative 2 is to the left of 0, so I want to be careful with that. Now, let's pick a number, right? Let's take a number to the right of 0. For example, 1. If I put 1 into my derivative, I'm going to have all positive numbers. So this will be positive. If I put a negative number between negative 2 and 0, I'm going to be negative. And if I put a negative number to the left of negative 2, I'm going to be positive. I could evaluate those, but once again, we said the multiplicity lets us know the sign will change if it's odd multiplicity. So change sign, change sign. Okay, so what does that tell us? That now tells us where we are increasing and where we are decreasing, right? So we are increasing if f prime is positive. So for this particular function, we are increasing for x values between negative infinity and negative 2, as well as x values that are going from 0 to infinity, right? Because here the derivative is positive and there the derivative positive. So then this means that we are decreasing, and we are decreasing if x is between negative 2 and 0. So let's write that a little bit more neatly. All right. Then we need to identify all the relative extrema, and we said f prime changes positive to negative, or f prime changes negative to positive. Therefore, we have a relative maximum at x is equal to negative 2, and we have a relative minimum at x is equal to 0. Let's write this negative 2 a little bit more neatly so it's more able to be read. And we want to identify the relative extrema, so we need the actual values. So we need to come back and say, what was our function? E to the 2x times x to the 4th. So therefore, the extrema is going to be negative 2 times, right, e to the 2x. So that's going to be e to the negative 2x times, we had x to the 4th, so that'd be 16. And we would have over here at x equals 0, and that would be e to the 0 times 0, which would be 0. So a relative minimum at 0, 0, and a relative maximum at negative 2, 16 times e to the negative 2x, which is a small number, but it's positive, greater than 0. Okay, continuing. Determine the open intervals on which this function is concave downward or concave upward. Identify any points of inflection. Justify your answers. We're going to justify to start. Once again, if that second derivative is greater than 0, then f is concave up. And if that second derivative is less than 0, then f is concave down. Right? We open upwards or we open downwards. And if f double prime changes sign, then f has a point of inflection. And it's okay to write POI. So we need to find these derivatives. Let's go ahead and do so. So f prime, our derivative is going to be negative 15 plus 18x minus 3x squared. And we want to figure out when that derivative is equal to 0. I personally don't like working with negatives for my leading coefficient, so I'm just going to rewrite this as 0 is 3x squared minus 18x plus 15, which of course can be factored as 3x squared, 3 times x squared minus 6x plus 5, which could be further factored as 3 times x minus 1, x minus 5. And for this particular function, we know that we're going to be equal to 0 if x is equal to 1 or x is equal to 5. But recognize, did we need to do that? We weren't asked for our critical numbers. We were asked about concavity. So that work we didn't really need to do. What we needed to do was find the second derivative to talk about concavity. And that second derivative, well, I can still play with the second derivative in the form, but it's going to be best if I use it from my initial part. And that second derivative is going to be 18 minus 6x. And we know that that's going to be equal to 0 if x is equal to 3. All right? So that's important for us. We'll now come in and do a sine analysis. Okay? So our sine analysis, we want to figure out what's happening with our concavity. So here we go. At x equals 3, that second derivative is 0. Okay, well, what if I have a number to the left of negative 3? For example, 2. Well, that's going to be 18 minus 6x. If x is 2, that's 18 minus 12, so positive to the left, negative to the right. So we know that we are concave down if x is greater than 3, and we are concave up if x is less than 3. Right? Second derivative positive, concave up. Second derivative negative, concave down. Then where is our point of inflection? Our point of inflection is going to be at 3, comma, f of 3. And we just need to figure out f of 3. Well, what does f of 3 equal? That's going to be 7 minus 15 times 3 plus 9 times 3 squared minus 3 to the third power. All right? If we evaluate, that's 7 minus 45 plus 81 minus 27. And that's good enough for us for our purposes. So now we have everything, and we have our justifications. Okay, now, of course, if we have an idea of what our graph looks like, here is a function that is a negative cubic. That negative cubic function looks a little something like this, and we know our point of inflection, and that point of inflection where concavity changes is when x equals 3. And guess what? We actually also know that this is when x is 1, and we also know that this is when x is 5. Okay, we got a few more problems to go through. Tried to go in a little bit more detail here so that you understand those details. Always reach out to ask questions as you need. Stick around and watch the next video for further help.